In Plait, we never actually have to write a type down. When we write lambda x like this, we don't have to put a colon question mark here to trigger type inference. We don't have to write the big lambdas to get polymorphic things. We don't have to write the @ signs to apply type applications. And one more thing we don't write down is the foralls and types. For this lambda xx, Plait will show quote a arrow quote a, and especially in Plait, I'll pronounce this alpha. It shows the type alpha arrow alpha instead of forall alpha, alpha arrow alpha. Now the type actually is forall alpha, alpha arrow alpha. It just abbreviates by not writing down the forall in much the same way that we don't write down the big lambdas. But there's a reason that being able to take this shortcut, not writing down the foralls, is justified. And it's tied up with the idea that a polymorphic function, it's not quite a function yet. If you have an f of type num arrow num, then of course you can apply f to 1. But if you have a polymorphic function, pf, that's forall alpha, alpha arrow alpha, then you can't apply pf directly to 1. First, if we're being explicit about our type applications, first you have to use an @ sign to specialize pf to the type number, then you can get a function back that you can apply to 1. Right? If you try to, when you're being explicit about @ signs, apply a pf directly to 1, it doesn't work because pf is not a function. Now this distinction between functions and polymorphic functions comes into play when we look more at type inference. So here's another example. I've got f and g, both let bound, so polymorphic inference can be relevant here. The function f takes a value v, and then it takes a function g, and it applies g to v. F doesn't care what kind of value v is, and it doesn't care what kind of value g is going to return, as long as g's argument type matches v's type. So the type inference for Plait will figure out that there should be two big lambdas here. One to pick the type for v, and one to pick the result type for g. G, meanwhile, down here is let bound to the identity function with no type specified. So of course this gets inferred to be forall alpha, alpha arrow alpha here. A big lambda is inferred there as well. Now it should be clear that we can, as a Plait program, call f with 10 and then pass in g as the function to be applied to that 10, right? And the way that this actually happens is that Plait figures out the @ signs, right? It figures out to specialize f to be the type of the value first, and then specialize that further to be the result type of g, and the result type that we want here is number, since g is going to be the identity function. Once we've specialized f in those two ways, then we can actually pass the value in 10, and then we need to pass a function in. But of course, f thinks g is a regular function, because it doesn't infer a polymorphic type for g itself. So g has to have a regular function type here. That means we need to specialize g to the type number instead of just passing in g by itself. Right? If, on the other hand, we said explicitly, if there were a way to say explicitly that g has a polymorphic type, then you could imagine calling f here, and we would not specialize g at this point. Instead, we would actually have to figure out a change to f to put the type application inside here. And then we can get even fancier. If we have a function that takes something with a polymorphic type, then of course we can use it in multiple different ways in the body of the function. But we've already said that Plait will not infer a polymorphic type for arguments. So if we took out this forall that we wrote, then Plait would reject the program. Here, it would infer an arrow type, but force all the argument types to be the same. So we have a mismatch between what we could write using forall and what Plait will infer. And the choice that Plait makes, following its predecessor language ML, it makes the choice that because Plait will never infer a forall type, you're just not allowed to write a forall type. That only, and that makes all the types that are going to be inferred consistent with the things that you could have written down. That also means that it makes sense to leave out the foralls because they're always at the beginning. If you can't pass, if an argument under an arrow here can't have a forall around it, that means all the relevant foralls are on the outside of the arrow, and so on for the other types. And since the foralls are all stacked on the outside, then you don't actually have to write them down. It turns out the order doesn't matter either, because if you picked a different order, then the inferred @ sign applications would just supply the arguments in the different order. So that's a constraint on the kinds of things that you can write with Plait or an ML, but it also makes all of the inference and the notation work out very conveniently.